Alright, so I'm testing to see if I have audio real quick. Apparently I do. And as I look at the screen, for some reason I had, let's see, there we go. Wait a minute. There we go. Let's make sure that this is going to take. Ah. Alright, now get everything set. Okay, we left off last time with a mistake that I had made, and I found it, and I tried to create a stream, but for some reason it didn't work last time. So here was my issue. My issue was that I came in here and solved that wrong, and I had a plus right here. So that was immediately wrong. Once I corrected that, then I end up getting the same value over here. So now that, you know, and I hope more than you paying attention to my error, that you pay attention to the fact that I was able to find it by checking along the way. Finding ways that you can make common sense of your problems as you go through this. Now, I need to go through the second phase here. Now, before I do that, let's identify all this mess on the screen. First, what I did right here was just purely straight up instant centers. I had a CAD drawing up last time, and I didn't save that CAD drawing, but ended up, calculating through sines and cosines these particular distances here. Well, I guess I'm sorry, it's not a cosine, it's just law of sines. Once I'm able to do that and recognize that this is the point in which everything seems to rotate about, I can quickly find the omega BC, simply because this one's already given me omega. Now, instant centers work great for velocities. They don't work at all for accelerations, which is why, for me, it's best to track down this path. Now, as I go through this, what I want to do is I want to pay attention to a couple things, okay? One is I've sort of crowded everything together. So what I might do is try my best to open them up here a little bit. And what I'm going to do is, let's see if I can use that. And I'm going to carefully go through here and select everything here. The computer is not very fast, and just slide it over to the right. Now, the reason I'm doing that is because I want to get rid of a couple things, and to identify there are two distinct parts to the problem that are completely related to the two distinct links. Here, well, And here's the two distinct link. Okay, so first you have link. Okay, if you look at the equations, you see A relates to B here. So I have one link right there. This one is the CB link. Now, since B is common to both, then I can work this out just fine here. Here, let me go to a different color. And the first thing I'm going to do is I'm going to go after this link. But instead of the velocities, now I have the acceleration of B is equal to the acceleration of B relative to A. This is the acceleration of point B if you were sitting on A, plus the acceleration of A. Go back up and look at this thing real close, and you'll realize that point A sits dead still. Point A is not moving at all. So previously we found that. And now we have a similar part that says this. Here is where things get a little different when we're talking about this term. Okay, we have what appears to be something very similar to before, meaning this looks like that, but it has an alpha here instead of an omega. That's the speed up. In other words, if you were running your car at 3,600 RPMs and it was staying 3,600 RPMs, then the alpha would be nothing. But if you're revving your car up and then letting it go back down, the alpha is positive, when you're going up, and negative when you're going down. Acceleration and deceleration. So alpha is the rate of change of your rotation, so to speak. But there's another term here. Okay, this term deals with the acceleration or the speeding up of the rotation. This term deals with the centrifugal component. And let me write this down and describe that for a second. That is, if your motor is spinning, and this is a point out here, in order for it, if it was going a constant speed, it would be going just off that direction. However, it actually goes around this direction. So as that point goes around this direction, something is changing, getting it to change its direction. The centrifugal component. And, that's the same thing as v squared over r, but this one is represented slightly different. Remember, v is equal to omega r. V squared would be omega squared r squared. So if I had v squared over r, I would end up with this term over r. Get rid of that. So then I would look, I wouldn't look, but it would look like that term. Okay, so let's keep going with this. If you go up here, you'll see he gave me my alpha. And it is, if you notice, that is positive. Remember the right-hand rule. So a rotation that just so happens to be counterclockwise is positive. I'm starting to get strange artifacts. All right. Okay. So, I've already forgot the number. It was 6. So if I were to represent this, it would be I, J, and a K. 0, 0, and a 6. So you might ask the question, what is that? Well, I already figured that one out. So I'm looking at the structure here so that I've already found out. Now remember, I've already checked the solution along the way and found the instant center gave me the same velocity here. So I feel comfortable that my analysis is okay. So now I just put those same values here, and give me a second here. I'm going to break out and use the octave like I was doing before. It's 9:13, so I need to really speed up a little bit here. And this thing is opening fairly large, which is not what I wanted to have happen. Okay. Remember last time here, let's do it this way. Alpha AB is going to be equal to, now this is, I'm going to write this as a vector. 0, 0, and 6. The RAB 0.5 divided by square root of 2. 0.5 divided by square root of 2. Then nothing. Now if I want to do a cross of alpha AB and RAB. Now, hang on a second. Let me find my pen. Okay, I ended up with and let me look at this, minus 2.1213 I plus 2.1213j. And this is the acceleration of B. Now, check along the way. If I multiply this number times this number, and then add that to this number, multiplied times that number, then essentially what I'm doing is I'm figuring out what this dotted with RBA is. I know by definition it has to be 0 because these two vectors are perpendicular. And again, why? A, B in 3 dimensions. Here's some C, which is equal to B cross A. Then those vectors are going to be 90 degrees to those. That's just the way a cross product is. So you have an opportunity to just glance half a second and you recognize, okay, in fact, this number, same size as that one. This one's same size as that one. The sign, different here. So it looks like we're good. Now I got to figure out how I'm going to get rid of that right up there, but I may just forget it and just leave it. Okay, now that I have that, I'm just going to go on. Now that I have this, I can just sort of hold on to it and say, okay, I got the answer, which is this. I'm going to use it in a little bit, but I've got to go over here to a problem that looks like this one. Okay, so what I'll do is, again, I'm basically going down link CB, and you could, if you wanted to, do something like this and say, I'll take the equation, I'll copy it, drop down here to the bottom, say right there, I'll paste it. That's not the equation I want, but what equation do I want? I want the accelerations now. Now, I can reach over here, grab this acceleration, and put it right in there, but I'm going to wait on that one and focus on this one. So I'm going to slide things over to the right. Acceleration of c is equal to alpha CB, which I don't know what that is, cross R CB, which I do know what that is, minus, remember this is the speed up term, and this is the centrifugal term, CB, BC. I'll do this way. Some authors will do CB, BC. It doesn't matter. The link is, these can be interchanged. The link is between those two. RCB plus, don't forget your acceleration B, which I'm carrying it along for the ride right now. Now what I'm going to do, I'm going to even make use of the structure I already had. Here's what I'm going to do. I'm going to go in here ever so gently, grab that term. I'm going to copy it. I'm going to slide down here. I'm going to say put it right around here maybe. Uh-oh. Put it, say, right around here. And what I'll do is move it right up under here and recognize that instead of this term, I need to have that. So I just need to change this. I'm having these strange artifacts again. Okay. Now, I've already figured out this. Looks to me like that length of that thing should be 1. Was that the case? And it was the case. So you can see the length is 1. That's why I don't have a leading. I have cosine and sine, but I have nothing leading there. So I've already figured that part out. Now here's the beauty of this system, okay? So now I have this, and now you might say, well, what happens here? Well, look back to a second ago, and you will find that here is the value of omega BC, 2.828. Is that right? Yep. Now, instead of just thinking about this, I can look right here and grab this, because this is, in fact, is this vector. So now I can just say cosine 60 I minus sine of 60 j. Why? Because I already did it. But now I have the centrifugal term. But I know the vector here, the vector here, are the same vector. Okay, and now I'm just carrying acceleration B for the ride. Now, I don't have this saved, but here's what I'm about to do. I'm about to do this cross product right here with the alpha taken out in octave. So here. This will be the last problem I work like this, and I'm moving on to the next sections after this. Okay, so I don't know. I'm going to be lazy. Cross. I'm going to drop the vectors right there. 0, 0, and 1. I'm going to cross that vector with cosine degree of 60 minus sine degree of 60. And so I put both vectors right there. I did not represent them off to the side. Now, is there, yeah, there is a, I looked for a minute and didn't see that comma. So this is what I get. I get 0.866 I with the alpha BC in front of it. And then I get 0.5 J. Now, if you want to, you can sit there and compare these things. You can look back up here. Whoops. And what you'll see is a comparative between this term and this term. Okay. You can also go in and do your dot products here. In other words, this times that plus this term times that term. So, in fact, if you do that, you'll find you're okay. Hang on. Now I need to go in here and I need to take, because this will be a numeric value, so will this, and so will this. So at this point, I'm going to take the time to go back and figure out what those values are. So give me a second. Let's see if I can find my mouse. There it is. So 2.828. You got to square that, and you got to multiply it times. First, I'm going to do times the cosine degree of 60. That'll give me one term. First of all, that wasn't a 2. That was a 1. 2.828. Try that again. Oh, geez, that's like almost 4. So let's just say that's 4. Okay, minus 4i. And this will be a minus, so the next one's going to be plus. And so the question is, what is the sine? That's not going to be so even. That's 6.92. Let's make it 6.93J. Still have to carry my B for the ride. So I'm carrying my B for the ride. Now, I'm going to take a look at something with acceleration of C. And I'm going to try to be careful here. In my drawing, I assumed, and this is the reason I do this. I always do it this way because if I don't know something, I'm going to make all references to this, meaning that this is where I'm going to assume that the acceleration is going to. It's going to the right and to the only x component. So therefore, just like I did right here with the velocity, but it disappeared. There it is. This will probably be the last time I use this particular laptop. I have 2 of them. Ironically, this is the more powerful one. But I think, okay, this time it turned from a vector to a scalar. And now I can just go ahead and combine this acceleration B. I'm going to drop it all the way down here and create the final equation. Acceleration C, it's going to get a little bigger, equals to alpha BC 0.866I plus 0.5j minus 4I plus 6.93j plus, now I'm going to go back and grab this. But if I do, it's going to be a minus 2.1213I plus 2.1213J. So I've got everything. So first thing I'm going to do, I am going to go in there and I'm going to say I'm going to go in there and I'm going to say look for my I components. Those are in blue. And the green ones will be my J components. And so I'll have a blue equation and I'll have a J equation. Okay, so I'll start, and well, you know what? I've never noticed whether you can, apparently you can. All right, here we go. Okay. So I'll start with my I equation. It's getting incredibly slow now. Maybe I can complete this out. My I equation, I have acceleration C equals to 866 alpha BC I, which I don't have to put, minus 4 minus 2.1213. My J equation, there's nothing on the left-hand side. There's 0.5 alpha BC on the right-hand side. That's my green, my next green. 0.693 and plus 2.1213. All right. Well, normally I would form two equations and two unknowns and solve them out. But it looks like I don't have to do that right here. Now, several day old memory, let me go back to the velocities and see if I got the same thing. Because if that's the case, I should have the same thing. Not the same numbers, but the same structure. Turns out with the J equation, I could do it straight up. So you see right here, you'll see the J equation gave me just that. I didn't have to form two equations and two unknowns. As it turns out, the structure is going to look very similar. The J equation does the same thing. So I can come up and determine alpha BC as being with a minus sign 6.93, because I had to move these to the other side, minus 2.1213 over 0.5. Let's see. Minus here. I'll just do it this way. 6.93 plus 2.13 1213 divided by 0.5 gives you minus 18. Probably good enough. Around minus 18.1. Now, I can go and take this and stick it in here, and 8.66 minus 18.1 minus 4 minus 2.1213. And so my acceleration of C will be, let me slide this down so I can do both of these at the same time. All right. 866 times 18.1 plus 4 plus 2.1213 Now, I kind of purposely dropped the minus sign, but they're all positive there, so it's going to be minus 21.8, it looks like. So, the question is, okay, first question is, what is this problem number? Oh geez, I did not copy the problem number down. Maybe I can open the book and it'll go straight to the page. And maybe it won't. Uh-oh. Either that's good news or bad news. But usually with a computer, okay, it's slow, so I've got to be patient. Okay, that, tell you what, let's do this. This may be both statics and dynamics book together. I could try this. Let's try this. Last time I tried that, it didn't work very well. So I'm not sure why this has an i7 in it, but for some reason the i5 seems to be faster, but the graphics here is the graphics component on this computer is much more computationally intensive, and so maybe that's the issue here. I don't know. Looks to me like I'd probably need to just give up this approach and just see if I can. And there's no real page number that I see, so I just keep scrolling, I guess. Oh, wait a minute. How did I go that far? Oh, wait. It's the statics book. Then it starts with the dynamics book. I'm getting closer. First thing is I just want to find the problem. Uh-oh. There it is. 16103. So that's where I started from. Let me go see if I can find the answer in the back of the book. 16103. I don't know if it helps to make it as small as possible. Oh, I think I reached the back of the book. 16103. I'm sorry to put you through the pain of waiting. Okay, so he says, you know what? Here's what I'll do. may have to wait a minute for that. Okay, good grief. Wow. That's what he says the solution is. I don't know anything. Oh gosh, it finally just, aha, I got a problem here. So I made a mistake. Let's see if we can track it down. Here's what I mean. Well, I got the, I got the velocity correct. Let's take a minute here and see if we can find out what I did wrong here, that I didn't get the 17.7 from. I got a 21. So let's first start at the most computations I did exist in this area. I feel moderately comfortable about this. I think I put in the 6, and I think I put the square root of, let's use the mouse. There's my 6, 5 square root of 2. And I got minus 2.12 and then a plus. So, oh my. Yeah. Massive, big time mistake. There is my mistake. I forgot that term. So, when it came to adding this, I've got 2 more terms that need to sit right here. Okay. Let me see if I can get that straightened out here. So first, I have this term. Oops. I have the 4 radians per second. Okay. So let me go in and sort of try my best at removing some of this extra. Usually you can just hit it. You can take it off of there. Oh no. Oh good. All right. Now, I am not done. Minus. Oh geez, I've already forgot. Was it 2 or 4? It was 4. Now, it was 4. It was squared. This term is the same vector that sits right there. So I have 0.5 over square root of 2i, and then I have now, so what I need to do, I need to figure out those 2 terms and add to these 2. Let me get down here. Luckily, the magnitude of each one of these is the same. So all I've got to do is calculate one of the magnitudes. And that would be 0.5 divided by square root of 2. And then turn around and multiply that times 4 times 4, which would be 16. And 5.6569. And then minus 5.6569J. Now, let's make sense of this, just that term. What is this term? This is the centrifugal acceleration. Now, it is if you look at the vectors, this vector, okay, let me zoom in on it a little bit. This vector, or this is actually the acceleration of point A as if, point B as if you were sitting at A. So if I were sitting at A, that's kind of silly, but here, let's look at this. The centrifugal acceleration of point B, let me get some of this out of the way. I'm going to have the component of the acceleration which goes exactly in that direction, which is related to alpha r. I'm going to have the component of acceleration here, that's the acceleration centrifugal, or my point being, it's negative in both the x and y. The other term should be positive in the y, negative in the x. Positive in the y, negative in the x. Negative in both the x and y. So sign-wise, it looks good. Now, what I need to do, carry it across and all the way down. So now I have to include, here's what I'll do. I'll just do it this way. Okay. Okay, you got to be kidding me here. Okay. A new computer that's this slow is annoying to say the least. I don't even know. I don't know what's going on here. Okay, so I'm going to do a copy. And I'm going to try to drop it right here. Oh, come on. Ah! Okay, that's good enough. We will definitely be switching back to the other machine. Okay, so what I need to do is take off those components from both. Minus 5.6569. See, it's just picking up, it's just randomly going berserk here. I hate Windows anyway. There is no reason that a Microsoft Surface tablet from Microsoft should be this annoying. Okay, Alpha. You're off on it because you need to drop out 5.6569. Move it down. Okay, I need to also 6569. Okay. There's no guarantee that this isn't the only problem on board here. So let's see if I can go up. Well, first of all, Even that, I mistyped. Let's see if I can get that. Hang on. Okay, let's do it this way because I've got a mixture of signs now. I got a mixture of signs, a minus and a minus. And I've written it incorrectly. It should be plus 5.6569. Okay. Fix, fix, fix. And the fix should be right here. 6 minus, let's see, minus 6.7 and a whole pile of 8s. Okay. Too lazy to subtract that. I should have gone back, and that would be a green, and this would be a blue now. And let me get back down here, and let's see. .866. Let's go ahead and put a minus sign in front of that. Times 6.738 minus 4 minus 2.121. Wait a minute. 2.1213. Did I do that right? 1213 minus 5.656967. No. Minus 17.65. How about 7? Yeah, 6. How about minus 17.66? What was it? Oh, okay. Yeah, and the fact that it's minus means, remember, I'm assuming everything that's going in the x is positive this way that I do not know. Everything that's going in the positive y direction here, and everything that's rotational is positive in that way, meaning that's why it's going to the left. That happened with the velocity as well. So mistakes can happen to the best of us. So I just plain forgot this term. And so just these are probably the most complicated problems you've got in this course. And they're not hard, but they do have the biggest opportunity for little errors like that. Omissions, minus sign changes, a variety of things. That's why you want to check everywhere you can check along the way. Unfortunately, there are areas like this one, for example, that don't necessarily have a check. So check where you can, and I think we're good for the day. Tomorrow we'll be back in the classroom. I'll be doing on the lecture on the board. I'm going to be moving into the next chapter, which is going back a chapter, several chapters, into the standard motion. This is the hardest chapter. The others will be deceptively simple compared to this. We're gone. I think.